powerful AI chip can be ready to do trillions of calculations and still sit there waiting, not because it is weak, but because the model cannot feed it information fast enough. That is the hidden reason AI needs so much memory, not just more GPUs. Faster chips help, but large AI models also need places to store their weights, their temporary notes, and the conversation history they keep checking while they answer. Most people imagine AI as pure math. Give the model enough processors and it gets smarter or faster. But running a model is also a logistics problem. The numbers have to be moved into the right place at the right time, again and again. Think of a GPU as a factory full of workers. Compute is how fast those workers can assemble products. Memory is the warehouse that stores the parts. Memory bandwidth is the width of the road between the warehouse and the factory floor. If the road is narrow, adding more workers does not solve the problem. The workers simply wait for parts to arrive. In AI, those parts are numbers. Model weights, token data, attention values, and intermediate results all have to cross that road. A language model is not a single program with a few rules. It is a huge collection of learned numbers called weights. Every time the model processes text, it uses those weights to transform the input into a prediction about what should come next. When a model has billions of learned values, those values must live somewhere while the model runs. If they do not fit in fast GPU memory, the system has to fetch them from slower places. That can turn a fast chip into a very expensive waiting room. AI systems use different layers of memory. The fastest memory is close to the chip, but it is limited and expensive. Larger memory, farther away, can hold more, but every trip takes longer. AI performance depends heavily on where the needed data is sitting. This is why data movement matters so much. Moving a number across a chip is cheap compared with moving it across a board, across a server, or across a network. The math may be impressive, but the travel time can dominate the real experience. During training, the memory pressure is even larger. The system stores model weights, intermediate activations, gradients, optimizer states, and batches of examples. Training is not just learning from data. It is constantly remembering the steps needed to adjust the model. But even after training is finished, memory does not stop mattering. Inference means using the model to answer users. The model still needs its weights loaded, and it also creates temporary memory for every active request. Text generation is especially demanding because the model usually writes one token at a time. It reads the prompt, predicts the next token, adds that token to the context, and then repeats. Each new step depends on what came before. If this kind of behind-the-scenes AI explanation is useful, consider subscribing. The goal here is not hype. It is understanding the machinery well enough to see why AI products behave the way they do. The key mechanism is attention. When the model writes the next token, it does not treat the prompt as a forgotten instruction. It compares the current position with earlier tokens, so it can decide which pieces of context are relevant right now. To avoid redoing the same work again and again, transformer models often keep a key value cache. This cache stores useful attention information from earlier tokens. It is like keeping index notes from the conversation, so the model can reuse them while generating the next token. The catch is that the cache grows with the context. A short question leaves a small trail of notes. A long document, a long chat, or a coding session leaves a much larger trail. The model may generate one token at a time, but its memory footprint keeps expanding. Long context sounds simple from the user side. Paste a book, ask a question, and expect an answer. Behind the scenes, the system must store and access information connected to many more tokens. The longer the window, the more memory must be managed efficiently. AI agents add another layer. They may search, read files, call tools, write drafts, check results, and continue for many steps. Each step can add more text, more tool results, and more state that the system may need to keep available. This is why memory is not just storage. It is the working surface of intelligence-like behavior. If the model cannot keep the right information nearby, it may slow down, forget useful context, truncate the conversation, or spend extra compute rebuilding what it already knew. Cloud AI systems also serve many users at once. Providers try to batch requests together, so the GPU does useful work for multiple people in parallel. But every active request brings its own prompt, its own generated tokens, and its own cache. A useful analogy is a hotel. The GPU is the building. Each request is a guest. Some guests stay for one night, and some stay for a month. If the hotel reserves huge rooms for everyone, space gets wasted. If it underestimates demand, guests cannot fit. Memory can also become fragmented. There may be enough total free space, but not in the right shape for the next request. Modern inference systems fight this by managing cache in blocks, similar to how operating systems manage memory pages. This is why AI speed is not only about the chip brand. Serving software decides how requests are scheduled, how caches are placed, when memory is reused, and how much waste is allowed. Good memory management can make the same hardware feel much more capable. For many language models, generating each token requires touching a large part of the model. If the chip keeps rereading huge weights from memory, then the limit may become memory bandwidth. The chip is not asking whether it can multiply. It is asking whether the numbers arrive fast enough. This can feel strange because the calculation for one next token may not fully occupy all the compute units. The expensive part can be pulling model weights and cache data through memory. In that situation, adding raw arithmetic power gives only limited improvement. That is one reason AI accelerators use high bandwidth memory close to the processor. The goal is not just more capacity, it is also a wider, faster path for feeding the chip. Large models need both room for data and speed for moving it. If a model or workload does not fit well on one GPU, systems split work across multiple GPUs. But then another problem appears. The GPUs must communicate. Moving data between chips can become the new narrow road, especially when many chips have to coordinate repeatedly. At cloud scale, the memory story spreads across the whole data center. There is GPU memory, CPU memory, local storage, networked storage, and high-speed links between machines. AI infrastructure is increasingly designed around placing data where it will be needed next. Sometimes systems offload data from GPU memory to CPU memory or storage. That can let larger contexts or more users fit, but it is a trade-off. If the model needs that data often, moving it back and forth may cost more time than it saves. Another strategy is compression. Model weights or cache entries can sometimes be stored with fewer bits. This can reduce memory use and data movement, but compression must be careful because the model still needs enough precision to produce reliable outputs. Some techniques reduce how much attention data must be read. Instead of checking everything in the same way, a system may use patterns, windows, or optimized kernels that avoid unnecessary memory traffic. The big idea is simple. Do the same useful work with fewer trips to memory. One famous lesson from modern attention algorithms is that memory access can be as important as the formula itself. By reorganizing work so data is reused while it is close to the chip, the same mathematical result can be reached with less costly movement. The same principle appears on personal computers. A model may technically run on a consumer GPU, but if the weights or cache spill into slower system memory, generation can become painfully slow. Capacity decides whether it fits. Bandwidth helps decide whether it feels usable. This also explains why long context can be expensive for AI services. A long prompt is not just more text to read once. It can increase memory use for the session, reduce how many users fit on the same hardware, and make every generated token carry more baggage. It also explains why two requests to the same model can feel different. A short answer to a simple prompt may be quick. A long agent task with documents, tool calls, and many generated steps may hit memory limits, scheduling delays, or data movement bottlenecks. AI hardware is being shaped by this pressure. Designers care about compute, but also memory capacity, memory bandwidth, chip-to-chip links, and ways to keep data close to where math happens. The winning system is not just the fastest calculator, it is the best organized machine. The business side follows the same physics. Cloud providers pay for accelerators, memory, networking, power, cooling, and idle time. If memory bottlenecks leave chips waiting, costs rise. Better memory use means more useful tokens from the same infrastructure. So the simple misconception is that AI scaling is only about buying more GPUs. More GPUs can help, but only if the rest of the system can feed them. Memory is where the model lives, where context accumulates, and where many real bottlenecks hide. The next time an AI model feels slow, expensive, or limited by context, remember the factory. The workers may be powerful, but the warehouse, the roads, and the notes on the workbench matter too. If you have questions, drop them in the comments, or suggest the next AI infrastructure topic.